In this video, we'll take a look at a new class of function called polynomial. A polynomial is essentially the sum of power functions, but we further require that the exponents be non-negative integers. So I have some examples here, and I've highlighted in blue the important parts of the polynomial as far as their definition is concerned. In this example, the exponents of x are 2 and 1. Here the exponents are 99 and 43. And notice it's just fine that many of the terms are missing. We don't have an x to the 98th power, for example. In this example, the exponents are 3 and 2, which are non-negative integers. The coefficients on the x's are rather strange. The square root of 2 and the 4 pi and the 2.4. But these numbers are allowed to be any real numbers. It's only the exponents that we've made a restriction on. Common examples that aren't polynomials are things with fractional exponents, like x to the 1/2, which is the same thing as square root of x, or x to the negative 1, which is the same as 1 divided by x. These fail to be polynomials because their exponents are not non-negative integers. We also frequently talk about the degree of a polynomial, which is the largest exponent that appears. And the leading term of the polynomial is that term that contains the largest exponent. So for example here, the degree is 2, and the leading term is x squared. Here the degree is 99, and the leading term is negative 4x to the 99. And here the degree is 3, and the leading term is square root of 2 times x cubed. So here I have another example polynomial. And if we look at the first graph, we notice that polynomials are capable of both increasing and decreasing in the same function. If you think back to all our other models, such as linear and exponential, logarithmic, all of these were forced to either increase or decrease. So power functions and polynomials have an extra degree of flexibility over these models. Polynomials can only change directions a limited number of times, however, and this number is related to the degree. A high degree polynomial can change directions many times, but a low degree polynomial can only change a few times. The second picture is a graph of the same polynomial, but at a much larger scale. When I allow the x-axis to range from negative 10 to 10, we can't see these tiny changes in direction. What you might notice at this larger scale is that the graph looks essentially like negative 2x to the 4th. And if we look at the definition of the polynomial, that's exactly the leading term. As the numbers get larger and larger, only the negative 2x to the 4th is important to the shape of the polynomial. The smaller x cubed and x squared terms become less and less important as x becomes larger. So when we think about polynomials, we want to keep these two viewpoints in mind. At the fine scale, there could be subtle changes in direction that are important for our model. But at the large scale, the polynomial behaves exactly as the leading term by itself would behave. So if we look at the fine scale picture again, we see that the graph crosses the x-axis at negative 1.5 and 0 and 1. These are called the roots of the polynomial. The roots have something to do with what's causing the function to change directions at the fine scale. We can actually determine what these roots will be just based on the algebraic expression of the polynomial itself. The roots will be easier to identify if we can factor the polynomial. So if I look at this expression, I see that each term has at least x squared in it. So I can factor the x squared outside. I'd like to factor the portion that's in the parentheses, but the negative sign on the x squared makes that a little bit difficult for me. So I'll factor out the negative as well. Now I'd like to factor this into two parts. I know that one of my factors will be 2x plus something, and the other factor will be x plus something. This is the only way I can get 2x squared as the front term. The two somethings have to multiply together to give minus 3. If this polynomial is factorable at all by hand, then I have to either choose 1 and minus 3 or minus 1 and 3. It turns out the one to pick is plus 3 and minus 1, because when I multiply everything out, this leaves me with a single plus x term. This factored form is useful for determining the roots, because if this last expression is equal to 0, then one of the three factors must be 0. So if the polynomial is to be 0, then either x is 0, that would correspond to the x squared term equaling 0, or x could be negative 1.5, in which case the factor of 2x plus 3 would be 0, or x could be 1, in which case the factor of x minus 1 would be 0. These are exactly the roots that we saw in the graph. There's a little bit more to see in the behavior of this polynomial, however. Notice that the function passes through the root at x equals negative 1.5, and it passes through the root at x equals 1, but it seems to bounce off the root at x equals 0. We can get some understanding about why this happens by choosing some random test points and evaluating the polynomial at these points. So if I were to randomly pick x equals -2, this is all the way to the left of all the roots. When I plug this into the function, I'm not really concerned with what number comes out, but rather just whether that number is positive or negative. So my color coding scheme here is that red factors come out negative and blue factors come out positive. So I have the negative sign out front, which is always negative. The x squared is always positive. And then for x equals -2, the 2x plus 3 is negative and the x minus 1 is negative. The result I have here is 3 negatives, which multiply to result in a negative. So plugging in x equals -2 gives us a y value that's negative, and that agrees with our picture. Let's move to the right just a little bit and plug in an x value that's between the x equals -1.5 root and the x equals 0 root. If I do the same kind of analysis, this time I see that I'm multiplying two negative factors together, and the result is positive. So choosing x equals -1 gives us a positive y value, which again agrees with the graph that we have. If I move a little bit to the right again, now I'm between the x equals 0 root and the x equals 1 root. And notice I get the exact same signs. The x squared is always positive, so it never changes from positive to negative. So again, I'm multiplying two negative signs together, and the result stays positive. The fact that the x squared is always positive is why we don't pass through the axis at x equals 0. Instead, the function decreases until it touches the axis, and then immediately starts to increase again. Finally, if we try an x value that's all the way to the right of all the roots, we get a single negative sign, and the result is negative. As we mentioned before, the large-scale view of this polynomial is that it looks essentially like -2x to the fourth. The terms with smaller exponents don't contribute when x becomes very large. The phrase end behavior refers to how the function behaves when x is a large positive number or x is a large negative number. So for this example, when x is approaching positive infinity, that is, when x is becoming a very large positive number, then y is becoming a very large negative number. Or we might say that y is approaching negative infinity. What this means in practice is that once we get past all of those roots, the function will be decreasing forever. What this means in practice is that once we get to the right of all those roots, the function will be decreasing forever. We also see that as x becomes a large negative number, then y is also becoming a large negative number. In other words, once we get to the left of all those roots, y will be decreasing forever. Polynomials typically arise in models when we're multiplying several small components together. So suppose we have a cardboard box whose base is square. Suppose we have a cardboard box and it's subject to the following constraints. Its base should be square, and the length plus the perimeter of this square base should be exactly 108 inches. Is it possible to model the volume of this box in terms of just a single variable? A convenient choice for our variable x would be the length of the square base. We could begin with the generic formula for volume. Volume is the length of the box times the width times the height. But we know the base is square, so if we say the width and height dimensions correspond to that square base, then w and h are both x, so we've reduced the number of variables. The other piece of information said that the length plus the perimeter of the base was supposed to be exactly 108. As an equation, this means that L plus 4x, which is the perimeter of a square with side length x, is supposed to equal 108. So I can rearrange this to express L in terms of the variable x only. So if I return to the volume function, I actually can express it in terms of a single variable. The length can be expressed as 108 minus 4x. The width is equal to x and the height is equal to x. So this expression is the factored form, or I could distribute the x squared to get a better picture of what the leading term looks like. So I can plot this function, and I see that when x is very small, we have a very long box with a very small base, which doesn't give a very good volume. As x gets larger, the volume starts to increase, but only up to a certain point. When x becomes too large, then we have a box with a very large base that's not very long, and this is also bad for the volume. So somewhere around 18 or so is the choice of x that gives the largest volume. If I zoom in a little bit, then I can be a little more confident that 18 is the correct choice. To prove that 18 is exactly the right choice is one of the great accomplishments of calculus. For now, we'll have to satisfy ourselves that if 18 is not exact, it's at least very close. So the maximum possible volume is just a little bit over 11,600 cubic inches. And in fact, if I plug 18 into the volume function, I get that the volume is 11,664 cubic inches. And the dimensions of the box that achieve this are 18 by 18, that's the square base, and then the length is 36 inches. I determined this by going back to our previous observation that the length is equal to 108 minus 4 times x. And since we've settled on 18 for x, I have 108 minus 4 times 18, which turns out to be 36.